Good morning. I'm Rakesh, and I'll be presenting my work on numerical simulations of quasi-1D nozzle flows. This study dives into the crucial aspect of gas dynamics, focusing on the modeling and simulation of nozzle flows, which are pivotal in aerospace and mechanical engineering applications. So, the converging diverging nozzle is a fundamental gas dynamics problem, which many of you may have found analytical solutions for in undergrad classes. Here, we assume that the flow is quasi-1D, a simplification which considers flow only along the axial direction and assumes uniform cross-section properties. This approach stems from real-world 2D flows like jet engines or rockets and makes it computationally feasible to analyze. Key scenarios at a throat nozzle depend on the geometry and boundary conditions. We may see three conditions, which include fully supersonic, fully subsonic, or supersonic flow with a normal shock, which we will explore in subsequent slides. Note that fluid properties at the reservoir are indicated with a naught or a zero, whereas flow properties at the throat are indicated with a star. So for the governing equations, we usually start with the integral form of the continuity, momentum, and energy equation, and then we arrive at the non-conservation forms of these equations in their differential forms. And since we have five unknowns and only three equations, we need two more equations to analyze this problem. And hence we can assume that the gas is calorically perfect, which eliminates the internal energy, as well as the equation of state, assuming that the gas is ideal, which also eliminates the pressure term. And hence we have three equations in three variables, making the problem feasible. So now we will also non-dimensionalize the variables to make the problem a bit more flexible for all design cases. So we divide the pressure and temperature by the values of the pressure and temperature at the reservoir. And for the length, we'll divide, I mean, the x dimension, we divide it by the length to make it non-dimensional. The velocity has been non-dimensionalized by dividing it by the reservoir speed of sound. And similarly with time, and note that the area has been non-dimensionalized by dividing it by the throat area, not the reservoir area. So we substitute all the non-dimensional terms to the continuity, momentum, and energy equations, and we arrive at the continuity, momentum, and energy equations in the non-dimensional form. And let us call this set of equations equation set 1. And so to find the finite difference equations, we'll be using McCormack's method, which is a set of four steps, which include the prediction step, the predicted values, the correction step, and the corrected values. So for the predictor step, we use the equations we got from equation set 1 and find the gradients of density, pressure, I mean density, velocity, and temperature by applying a forward difference to the equations. And using these gradients obtained in step 1, we find predicted values for the three variables. And using the predicted values, we now apply a backward difference to the equations we got in equation set 1, and we find yet another gradient. So using the two gradients we have obtained in the corrector and the predictor step, we find the average gradient of the backward and forward differences, and we find the value of the variables at the next time step by using this average gradient. So with regards to the boundary conditions, the inlet of the nozzle is always subsonic. So we set the pressure and temperature to 1, or which is equal to the reservoir conditions, whereas the velocity approaches 0, and we can't set 0 as a realistic value, and hence we just find the velocity at point 1 from linear extrapolation. And since we can have different types of exit conditions, we'll just extrapolate all of the values at the exit or the efflux boundary. So for the supersonic case as well as the shock case, we'll need to consider a quadratic profile for the nozzle geometry. This is to ensure that there is choking or that the velocity approaches Mach 1 at the throat at x equal to 1.5. Whereas for the subsonic condition, we don't want the flow to choke, and hence we'll have to consider a different geometry. So moving on to the results. For the supersonic condition, we ensure that the flow is smooth, and hence, since the velocity chokes at the nozzle throat, we ensure that the flow keeps accelerating throughout the nozzle. And since the nozzle is an expansion device, an increase in velocity is accompanied by a decrease in pressure. And thermodynamically, a decrease in pressure is also associated with a decrease in density as well as temperature, as shown. So for the case of subsonic conditions, since the velocity does not choke at the nozzle throat, we find that the velocity decreases in the diverging section. And since there is a velocity decrease, according to Bernoulli's law, we find that the pressure increases in the diverging section, and so does the density and the temperature. Now, with regards to the normal shock, a shock is described as a discontinuity in the flow field, and shocks usually increase the pressure of the flow. So, although the flow does choke at the nozzle throat and continue to supersonic conditions, the sudden shock does reduce it back to subsonic flow. And the sudden shock or the sudden drop in velocity results in a subsequent sudden increase in pressure, temperature, and density. So, in summary, this work demonstrates the effective numerical simulation of quasi-1D nozzle flow using McCormack's method. It also highlights the method's robustness in capturing shocks. However, to fully understand supersonic phenomena, 2D simulations are the logical next step, especially for analyzing complex events like oblique shocks and Prandtl-Meyer expansions. Thank you for your attention. I look forward to any questions or feedback you may have.